Good afternoon, everybody. I'm Piyush. I'm a PhD student at ANU, and today I'll be telling you about some of the theoretical works that we have been doing to model spatially resolved gas phase metallicities and metallicity gradients. So the reason why we would want to do this right now is because of this amazing data set that is coming out of integral fields unit spectroscopy, where you can really look at spatially resolved regions of a galaxy, even in the metallicity space, and figure out the metallicity history as well as evolution in galaxies. So the way you would do this normally, at least in a 1D or a radial sense, is shown in this figure here, for example, where you see the image of NGC 2997 and color coded by metallicity in different H2 regions that have been identified in this galaxy. So go in any particular radial direction, you measure all the metallicities of the different H2 regions that fall in that direction and sort of get a 1D radial gradient out. And this radial gradient, the metallicity gradient, has been the subject of a lot of really interesting research in galaxy evolution that has happened in the last decade. With these observations coming up, simulations are also starting to catch up. So we now have simulations like Illustris GNG and Eagle and several others, where people can measure metallicity maps in the gas phase in galaxies and draw similar radial gradients. And then that sort of tells a nice comprehensive picture of the metal budget of galaxies, which motivates understanding the physics behind these metallicity variations and gradients. So we have developed a new model for metallicity gradients from first principles. And the model sort of relies on this bathtub model of chemical evolution that is very popularly known in the literature, where you have some sort of very metal poor or pristine gas inflowing into the galaxy in here, which triggers star formation. Star formation will then produce metals, and metals will then be returned back to the interstellar medium on different time scales from supernovae as well as AGB stars and so on. And throughout this process, this happens all in tandem. So you continue accreting gas from the cosmic web, you continue doing star formation in the galaxy, and then you're continuously ejecting metals through winds and outflows in the galaxy as well. But something that this particular picture misses is the involvement of radial inflows. So basically what that means is galactic disks are very dynamic. So gas as well as metals in the gas in these disks are not stationary. They're continuously moving and inflowing throughout the disk. So it's important to take the radial motion or the radial inflows of gas and metals into account. Metals also diffuse in galaxies, and diffusion of metals has been the subject of very recent simulations, but that has not been explored at all in theoretical models that deal with galactic chemical evolution. Something else that is commonly assumed in several existing galactic chemical evolution models is that the enrichment of metal outflows is negligible. So what that means is if you measure the outflow metallicities, it sort of turns out to be the same as the ISM or the galactic metallicities. And very recent works led by, in fact, some of the people in Astro 3D have pointed out that this might not necessarily be the case, which means the outflow metallicities may not be the same as the ISM metallicities. So we drop that assumption in our models. So when we have radial inflows as well as metal diffusion, we can now include all major modes of metal transport on galactic scales, which means that we can now apply this model to a wide range of galaxies, both in the local as well as the higher redshift universe. And in the applications of the model that I'll show you today, the thing to note is that we'll not be fitting any of the model parameters to the data. And the reason this is not required is because the metallicity model is connected to a galaxy evolution model. So the parameters of the model are more constrained by galaxy evolution and how galaxies are evolving rather than the data itself. So I'll talk about the local mass metallicity gradient relation, or the MZGR, as I call it. This figure shows how the MZGR looks like for the model. So the y-axis shows the metallicity gradients as a function of the stellar mass for different local galaxies on the x-axis. And the color bar denotes the ratio of radial inflows to gas accretion. So if you are on the redder part of the map, radial inflows dominate over gas accretion to set metallicity gradients. Whereas if you're in the bluer part of the map, accretion of gas dominates over radial inflows to set metallicity gradients in those galaxies. And there is a transition region in between where both of them are sort of equally contributing to different things. The length of these different color bars that you see on the plot tell you about the enrichment of metals in outflows. So if you're at the top of these color bars, it means that the outflow metallicities are really high as compared to the ISM metallicities. So which means that the galaxies are preferentially ejecting a lot of metals in their outflows. If you are towards the bottom of these color bars, it means that the outflow metallicities are the same as the ISM metallicities. So there is no preferential ejection of metals from the galaxy. And the metals are well mixed in the galactic disk before they're ejected. So now what I'll do is I'll overplot data from the well-known SAMI, MANGA, and Khalifa surveys that also plot the same MZGR. And this is where the data looks like. So the orange markers denote the 3 different surveys, and the gray markers is sort of a mean of all of these 3 surveys. And there are a number of interesting things we can learn from this comparison. The 2 key points are that we see galaxies transitioning from an radial inflow or an inflow dominated regime to an accretion dominated regime as they increase in stellar mass. And the transition between these regimes sort of occurs around the location where the MZGR shows a curvature. We also see that all the low mass galaxies in all of these 3 surveys individually, as well as that combined mean, these tend to lie towards the top half of these color bars, which means that low mass galaxies are preferentially losing more metals in their galactic winds as compared to high mass galaxies. Another thing that we can do is not only look at the metallicity gradients, of course, but we can also look at the integrated or the global metallicities of galaxies together, which is already very well known as the mass metallicity relation, or the MZR. But something that is not really explored is how does the metallicity gradient look like as a function of the global metallicity in local galaxies. So this is the results from the model, where the color bar now is the stellar mass of the galaxy, the y-axis is the metallicity gradient, and the x-axis is the total metallicity. And the different lines, the different curves that you see represented by the different shapes of the markers denote the metallicity of galactic outflows. So if you are on the top left, you have very metal enriched outflows. If you're on the bottom right, you do not have any metal enrichment in the outflows again. So I'm not aware of any data that has looked at this parameter space in particular, which means that the model has some predictions that can be tested against observations that are already available, which is that galaxies should lie along a bent track in this particular space. So you can see no matter which curve you choose, they all bend around the transition mass in this particular parameter space. And all of the massive galaxies show flat metallicity gradients regardless of the nature of their winds. So it doesn't really matter if the winds in massive galaxies are metal enriched or not. They should show flat metallicity gradients, which is consistent with the observations we have. So to summarize, we have developed a new model to understand the physics behind gas phase metallicity gradients. And the model includes a bunch of things that were not included so far in existing models. And then it can be linked to a galaxy evolution model so that both metals and the gas can be treated self-consistently. Some applications that I've covered in this talk are on the local universe, the mass metallicity gradient relation, as well as the MZR and the MZGR space. And we find that galaxies transition from an inflow-dominated regime to an accretion-dominated regime as they increase in mass. Low-mass galaxies preferentially would lose more metals through galactic winds. Massive galaxies should show flat gradients regardless of the nature of their winds. So this analysis is really focusing on how galaxy chemical evolution is not a closed bathtub model at all, and you really need inflows as well as outflows and accretion to understand the entire metal budget in galaxies. There are some other applications of the model that I have not covered in this talk, but please feel free to ask me about them in questions or check out these papers where all the details are given. Thank you very much.
Thank you, Piyush. That was an excellent talk.
Thanks.
Yep, again, we've got a lot of questions in the Slack. So first up from Katie, you mentioned the importance of radial inflows and disks for mixing of the metals in the ISM. Does the impact of this depend on the type or strength of spiral features? For example, grand design spiral arms versus flocculent spirals with ill-defined arms, or other galactic features such as bars?
Right. So radial inflows will definitely be influenced by the presence of spiral arms and the strength and the variations in spiral arms, as well as definitely by features like bars and so on. The radial inflow model that we use is from Mark Krumholz's 2018 unified disk model, which does not differentiate between bars and spiral arms. It's a 1D analytical model, but this could be done through simulations for sure. So I definitely expect that radial inflows will be different in different galaxies based on these morphological, like the presence of bars or spiral arms, for example, but the model here does not take that into account. Yeah.
Sure, thanks. And just one more from Deanne. Really great work, Piyush. Do you consider differences in metallicity of inflowing gas from galaxy to galaxy, which could correlate with galaxy mass?
So far, for the results that we have worked on, we have assumed that gas accretion onto the galaxy is pristine. So it's very, very metal poor. But if you take, for example, things like fountains into account, you can have metal enriched gas falling onto the galaxies as well. And that will be the next step to consider in such a study. You also include fountains and not only inflows and outflows separately. Yeah.
Great, thanks. And there is one more, but I'll leave that for you to answer in the Slack.
Thank you.
Cool. Thanks again.